Polarity is an unequal sharing of electrons. We care about this because we're going to concern ourselves with the resulting effect on molecules. Electronegativity is the ability of an atom to attract electrons when in a chemical bond. Notice that electronegativity increases up to the right, fluorine with the highest value. It's likely that you would not have access to an electronegativity table on an AP exam. You should assume that bonds made with two different atoms are polar, except for carbon-hydrogen bonds, which you should consider nonpolar. A nonpolar covalent bond, the electrons will spend their time fairly evenly distributed between the two nuclei. But as a result of a higher electronegative atom, the electrons will spend more time near one atom than the other. How can we symbolize bond polarity? We will utilize an arrow with the point end of the arrow pointing at the more electronegative atom. Or we could use this plus minus, this lowercase delta, to symbolize partial negative and partial positive charge. The hydrogen and halogen series, hydrogen bonding with fluorine, chlorine, bromine, and iodine. Larger halogen atoms will result in a longer bond length, and larger halogen atoms, because the outer valence electrons are so far from the nucleus, will have a lower electronegativity compared to hydrogen and fluorine. This results in a difference of electronegativity much smaller for hydrogen and iodine compared to hydrogen and fluorine. Polarity is measured with a dipole moment. The units are measured in dBs, and a less polar molecule will have a lower dipole moment. A more polar molecule will have a higher dipole moment. The key to understanding polarity is being able to draw a Lewis structure. This is first and foremost. You should take the time to pause the video and practice drawing Lewis structures if you need to. Again, we'll assume that two different atoms will be polar, unless, of course, it's a carbon-hydrogen bond, in which point we will consider it to be nonpolar. You'll only be asked about the polarity of molecules, not polyatomic ions. So, assuming you can draw a Lewis structure for carbon dioxide, the next most important factor is to consider the electron domains surrounding the central atom. In the case of carbon dioxide, there are two electron domains, and thus these two dipoles are symmetrically opposed in opposite directions, with the negative end as the oxygen, and this linear geometry will cancel out the two dipoles, resulting in a nonpolar molecule. With sulfur dioxide, if you can draw a Lewis structure, you'll see that there are three electron domains on the central atom. These three domains will be arranged in a trigonal planar geometry, but the one unshared pair will cause a bent molecule. This will result in the two dipoles not symmetrically opposed and will not cancel out, resulting in a polar molecule. Water, H2O of course, we want to be able to draw the Lewis structure, and notice that around the oxygen there are 4 electron domains, which would be arranged in a tetrahedron. But importantly, the two unshared pairs cause a bent molecular geometry, and those polar bonds are not symmetrically opposed and will not cancel out, resulting in a polar molecule. Again, drawing Lewis structures is most important. In ammonia, there are 4 domains around the central nitrogen, arranged in a tetrahedron. However, the one unshared pair will cause a trigonal pyramid molecular geometry in which the NH dipoles are not symmetrically opposed, will not cancel out, resulting in a polar molecule. In formaldehyde, CH2O, notice there are 3 electron domains, resulting in trigonal planar geometry. However, the 3 bonds, 2 of the 3 bonds are not the same, resulting in a dipole not canceling out, and the molecule will end up polar. The CF4 bonds are very polar, 4 domains surrounding the central carbon, resulting in 4 dipoles that are symmetrically opposed in this tetrahedral geometry, and they will cancel out, resulting in a non-polar molecule. Again, important to be able to draw a Lewis structure. You may have drawn this structure for CH2F2, or you may have drawn this structure. Do not be fooled by this structure. Many students may think that these 2 dipoles would cancel out. However, this molecule is a tetrahedron, and the CF dipoles cannot be in opposite directions, cannot be opposed by each other, and will not cancel out. This will result in a polar molecule because they cannot be opposite the way this implies, may lead to incorrect conclusion. So the molecule will end up polar towards the fluorines. A little bit easier in the molecule below, where there is only 1 fluorine, resulting in a single dipole. Pick any one of the tetrahedron and will not be symmetrically opposed by the non-polar carbon-hydrogen bonds. This will result in a polar molecule. Again, cannot overstate the importance of drawing correct Lewis structures. In propane, the CH bonds are all geometrically opposed, not to mention that they're nonpolar, resulting in a nonpolar molecule. In propanol, the oxygen-hydrogen bond or carbon-oxygen bonds will be polar bonds. And importantly, notice that there are 4 domains around the oxygen. Those 4 domains will result in bent geometry, the 2 unshared pairs, with polarity in the direction of the oxygen, and this molecule will be polar. The polar OH bonds and CO bonds will not be symmetrically opposed and will not cancel out. The same thing will happen with acetone, with the 2 unshared pairs on the oxygen, once again resulting in bent geometry, and the carbon-oxygen bonds will not be symmetrically opposed, will not cancel out, again resulting in polar. 6 electron domains, resulting in 6 dipoles in an octahedron, that will be symmetrically opposed, resulting in a nonpolar molecule. The next two molecules both have 5 domains around the central atom, and the 5 domains, arranged in a trigonal bipyramid set of domains, but with one unshared electron pair, will result in the seesaw molecular geometry, which will not be symmetrically opposed. The resulting dipoles will not be symmetrically opposed, and the molecule will end up polar. Again, with 5 domains in which 2 unshared pairs occur, the molecule will end up T-shaped. The CLF bonds, which will be polar, of course, are not symmetrically opposed, will not cancel out, resulting in a polar molecule. PCl5 has 5 polar bonds arranged in a trigonal bipyramid. Those will all be symmetrically opposed and will cancel out, resulting in a nonpolar molecule. With 6 domains arranged in an octahedron, however, with one unshared pair, will cause square pyramid molecular geometry. The BRF dipoles are not symmetrically opposed and will not cancel out, resulting in a polar molecule. In this direction. Again, drawing Lewis structures. The XEF has 6 electron domains. However, the 2 unshared pairs will be at opposite sides of the octahedron, resulting in a square planar geometry in which the dipoles are opposed. They will cancel out. The molecule will be nonpolar. All 4 are arranged in a planar arrangement and will cancel out and end up being nonpolar. With KRF2, there are 5 domains around the central atom. The unshared pairs distribute themselves in the equatorial positions, the 3 unshared pairs, resulting in a linear molecular geometry in which the 2 dipoles will be symmetrically opposed, will cancel out, ending up in a nonpolar molecule. It's very important to realize that the unshared pairs will be in the 3 equatorial positions, again resulting in the linear geometry.